is on the concept of what are known as RC circuits. In RC circuits, as the name might imply, which it does, is a resistor and a capacitor hooked up together. Let's imagine the resistor is not here, right? And we have this capacitor that's been charged, and we flip our switch here, and what happens is we've learned previously that this capacitor will discharge, and if we have an amount of charge on there that's pretty pretty standard charges on here, nanos or micros or things like that, we worked out when we started to introduce current that this discharges very, very rapidly, nanoseconds. Okay, great. Now, what if we throw a resistor in here? If we throw a resistor in here, one of the purposes of the resistor is to provide a resistance, right? And so what happens is if you close the switch and the resistor is connected, this capacitor is going to discharge, but it won't not be able to do it as fast as if it were without one there. And so this basically creates, having a resistance here, basically allows us to create a circuit that has the timed element in it. Because this capacitor will take a certain amount of time for it to discharge. And there's a lot of really interesting uses for this. I mean, a couple things I can say. One, the whole idea of the resistor limiting the amount of current means that you can create a particular signal and let it last for a given period of time. So what's going on here? Let's do a loop law. Let's just do loop law. We have a potential difference across the capacitor. So if we do a loop law here, we have our potential difference across the capacitor, which will be a potential gain because of the charges here, and then we have a potential drop across the resistor. And that's all we have here. So to express the potential difference for the capacitor, that is given by the capacitor equation. So it's going to be Q over C. And the resistance is given by Ohm's law, which is going to be minus IR. Now here's where it gets kind of interesting here. We have an equation that has an expression for Q, just the amount of charge that's on here. And we have I in here, which is a time derivative of Q. So guess what that means? It is technically a differential equation because the current depends on the charge, but the amount of charge depends on the current because the current's telling you how much you're discharging, but then that determines. So when you have this, the concept behind the differential equation is you have a quantity that depends on another quantity, but it depends on that first quantity as well. So you have this constant change taking place. And so what we want to do is we want to rewrite this purely in terms of charge. Now, we've got to be careful about this, though. This Q that's in here corresponds to the charge that is on the capacitor at some moment in time. So it's an instantaneous value for the capacitor. So if I'm going to express what the current is here, I'm going to express it as a negative dq dt. And you want to say, why is it negative? It's because this Q is referencing the Q on the capacitor. And the rate at which the charge is dropped, well, the rate of the change of the charge is that it's dropping. It's going down. So we'll need a negative here. So we're going to make that substitution. In this equation up here, we're going to put a minus dq dt. Okay, so now the Q's are the same Q's, because again, this is not the Q that's going through the resistor here. That's not what we're talking about. I mean, that is what current is. Current is describing the change in, Q over dq dt, but in the equation, the Q is referenced in the capacitor, so we put the negative sign there so we are ensured that we're talking about the same Q's. All right, so with that substitution, we can rewrite that equation that we had there. This is the loop law equation. We divided this by R, Okay. We separate the terms. We do the separate the differentials. Don't tell a math instructor I did this, but you can kind of do it. But don't tell a math instructor I did it because they get all they get all stickler for rules. Well, you can't break up a derivative. Whatever. Okay, you can do it. So if we integrate this, the left-hand side becomes a logarithm, right? And, well, we'll just say ln q. And the right side here becomes a t over r. We're going to take that logarithm, excuse me, and we're going to turn it into its exponential form. So in its exponential form, instead of an ln, we're going to have e to the minus t over tau. Now, the tau in this context here is what we call the time constant. It's given by r times c, which, interestingly enough, ohms times a farad somehow comes out 2 seconds. That's really strange, but if you kind of dissect what all those units ultimately are, you do get a seconds out of it. Seems odd, but it is. Now notice my limits of integration on my charge here went from q naught to some later q. Again, because we start off with an initial charge on the capacitor, and then it discharges over time. So the final q is some smaller value of q. And anyway, we end up with the following relationship here. Now, let's explain a little bit about what's going on here. This is, at its core, exponential decay. So the capacitor doesn't discharge instantaneously. It discharges as exponential decay. And the time constant is very interesting for us because the time constant is basically a measure of the rate of the exponential decay. And if, for example, well, you know, I guess I'll explain it as we move on, do some examples of this, but I'll just say real fast. When you work out what your time constant is, when you get to that time, say your time constant comes out to be, I don't know, like a millisecond. What that means is when you reach a millisecond, the charge will drop to 1 over e's value, which is 0.37, I believe. 1 over e is a number. I know it's a number. What's that number though? It's like 0.3678, blah blah blah. So it's like 0.37. So after one time, you know, is that my next slide? Because if it's my next slide, I'm gonna be kind of mad at myself. I mean, I'll be happy and mad. Look at that. Look at that. I'm happy because my mind, way back in the day when I made this, is the same mind I have today. Hopefully. But the bad thing about it is that I should just got right to this. So anyway, this is the mean of the time constant. That after one time constant passes, you have now dropped to 37% of the initial charge of the capacitor. And then after 2 time constants, you drop down to 13%. Okay, now what is e to the third? 5%. And e to the fourth is 2%. And so e to the fifth is less than 1%. So what that means is after 5 time constants have passed, you effectively have discharged your capacitor. Obviously not completely, but you're less than 1% now of the original charge. And that's effectively 0. It's not 0, but you know, it's effectively 0. So that's interesting. And of course, the way that this line is, I don't like to use the word sloped, but the rate at which this, you know, the curvature here is going to be dictated by tau. So it's altered by having a different resistance and a different capacitor, right? If you were to up the resistance, your time constant goes up. That makes sense because a higher resistance means less current can be drawn, so it will discharge slower. If you have a higher capacitance, again, that means a higher time constant, which makes sense because more charge would take a longer time to decay. So that makes sense. This is nice. This is nice. Very nice, actually. All right, students. We have two RC circuits here. Which one is going to discharge more quickly? A and B and 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 A and B. That's not an invitation to put another letter in, by the way. So it's either A or B, huh? Well, let's look here. What's the time constant for the top one here? What's the time constant for this one here? 6 times 2. 12. 5 times 3 is 15. All right, so this does have a higher time constant down here. So the answer is A. Because with 12 here, in, say, what is it going to be? It's going to be 12 microseconds, this one, 12 microseconds. So in 12 microseconds, this reaches 37%. But down here, it'll take 15 microseconds to reach that 37%. Having a smaller time constant means you're going to discharge more rapidly. Okay, this one's going to discharge slower. Okay. Great. Now, so we have a statement for what the charge in the capacitor is. Well, we can use our familiar laws to come up with some other statements as well. Now, the relationship between charge and voltage in a capacitor, they're directly related. All right, it's the voltage. I don't have my, what did I do with it? Oh, it's in here. Get this plugged in. I got all organized over the weekend. So I put things in places that I don't remember where I put them. That's the bad thing about being organized. Is that when things are everywhere, they're easy. When you put everything away, and you start screaming at your family, who stole my drawing tablet? All right. So the potential difference, right? Q over C. So they're directly related. So guess what you do to change this equation into one for voltage? You divide both sides of this equation by C by C. And there you go. You got your potential equation. All right, so if we want to figure out what the current is, right? Current is given by dq dt, right? But remember, we're using with the negative sign in the front because we're relating it to how the capacitor behaves. So if we take the derivative of our expression at the top here, we get a negative. On the front, we divide by a tau. That's taking the derivative of the exponential. It returns the same function except with the coefficient of the variable out in the front, which changed that tau to an RC. Q naught over C is the voltage, the initial voltage, and delta V over R is, from Ohm's law, the initial current. So now we have these three relationships now that all look identical to each other. They pretty much are. And this will completely explain the behavior of the circuit here. What this means is because the equations for the potential difference and the current are the same, then the same thing we described about the charge is the same. So after one value of tau, the value of the current reaches 37% of its initial value, the charge of the capacitor does, and the potential difference across each element does. Okay, fantastic. Let's do a problem. We want to know what the time constant is for the capacitors here. Now, I mean the capacitors and the resistors here. Okay, so this is a combination problem. We got parallel capacitors, right? So parallel capacitors, oh, I guess I should bring up my... the capacitors are in parallel. right? And remember that this is a little confusing, obviously, but the rules for series and parallel for capacitors, right, are different than they are for resistors. So the parallel capacitors have the additive inverses. So it's going to be now two. Wait, what? Oh, I mixed that up here. Okay, sorry. So the parallel capacitors, they add up. So that's 2 microfarads and 2 microfarads. The parallel resistors, though, they have the additive inverses. So that's 1/1000 plus 1/1000. Okay, so we work this out. We get 500. We work out the capacitor ones. We get 4 microfarads multiplied together. 2000 micros is 2 milliseconds. And so this particular RC this particular RC circuit, while it's a combo, behaves as if it's a single resistor, single capacitor with a 2 millisecond time constant. All right. Is it the same one? Oh, brother, it's the same one. All right, so we have the same RC circuit we had before, 2 milliseconds. And we want to know if both capacitors are initially charged to 45. Oh, that's interesting, actually, because if they're both charged to 45, that means their equivalent one is charged to 45. Now, if I did something silly here and I decided to make them series and I told you that, then the answer wouldn't be 45. If the capacitors were in series and I said they're both initially charged at 45 volts, you'd be putting 90 in here because the series, the potentials add up. But this is a parallel thing, so they have the same potential difference, 45. So how long after closing the switch will the potential across each capacitor be reduced to 10 volts? So 10 is my final value. My initial is 45. And I have to solve my exponential up here. So I'm going to take the natural log of both sides. And not going to get too much into the math here, but the negative sign disappears because this is actually ln 10 over 45. But if you flip the argument of a logarithm, right, that just makes it negative. So the negatives cancel out. And so this turns out to be 3 milliseconds. And then we know what the current's going to be. We're going to go through the same process here. So we want what the initial current is in order to do this. Well, that's going to be given by delta V over R, where R is going to be the equivalent resistance. So because these two things are in a parallel, we're going to do the additive inverses. And so this is going to be 500 down here. So 45 over 500 is our initial current. We're going to put in the time we got from the earlier part, and we get our current to be 0.02 amps, which we're in between 1 and 2 time constants. 1 and 2 time constants. So we're probably somewhere around like 20% of the current or something like that. I mean, let's see what it is actually. 45 over 500, 0.09. So yeah, it's like 22%. All right, sounds good. Sounds good. Let's keep going. All right, this is a great question. All right, now what we're going to do now is we're going to throw a battery into this. We're going to throw a battery into this. So we're going to see how things behave with a battery in there. Because before it was just, we have the capacitor charged, and we're not going to question how it's charged. And now we put a battery in there, we can now look at not discharging, we can look at how it charges. So, question for you here. Probably saw the answer already, but if we close the switch here, what is the capacitor voltage? I'm just kidding, it is A. All right, now the best way to think about this is what determines what the potential difference across the capacitor is, right? It depends on how much charge is on the capacitor. But the minute you close a switch, the capacitor doesn't have the ability to just instantly charge. In fact, if my resistor wasn't here, the answer would still be A, actually. The difference is that with the resistor not there, it would take like a nanosecond for it to charge. With the resistor there, it's going to take not some amount of time. Like this time constant here is 15 microseconds. So 15 times 5 is 75 microseconds. It's like 99% charged after 75 microseconds, right? So anyway. So now, when we are dealing with charging, as you might suspect that this is going to have a exponential relationship as well, but it's what we refer to as an upside down decay. So what we're doing here is we're taking our exponential function, we are flipping it across the time axis, and we're shifting it up 1. Now mathematically what's going on here is loop law is a little different now. Loop law has a potential for the battery, the resistor, and the capacitor. And in this equation here, the 1 comes from the fact that the battery is in here. And so there is sort of an asymptote here. I can draw that out. This nice green, lovely green. There you go, like that. And so what happens is you initially have no charge, and then it starts to charge kind of rapidly, and then it starts to slow down. And same deal, when you get out to about 5 time constants, you've effectively reached full charge. It's like 99.3% or 4% or something like 99.4% or something like that. So that simply comes from having the battery there, and the battery is going to be used to charge this thing. All right. Same principles apply to everything. It's just this extra, there's an extra term for the battery, and that's where the 1 comes from. So, okay. Question for you here. We have a battery hooked up to in our RC circuit, so we're going to charge our capacitor in this way. So how do you think the red curve that you see here is how the upside down decay is going to happen. But if we were to, say, change the resistor by, say, lowering the value of the resistor, how do you think this is going to change? B's? Is it because I'm screwing up my screen share again? No, it's not. Really? Why is it? Well, there's some C's and A's, but the answer is B. What's special about B? B reaches the same final value of the charge. Now, here's the thing. We're not changing the battery, and we're not changing the capacitor. After a very long time passes here, there's going to be no more current flowing through here. And that means the resistor is effectively eliminated from this thing, and whatever potential difference exists across the battery, the same potential difference will be across the capacitor, meaning we will still reach the same final charge. The same final charge. So, just based purely on the fact that it terminates the same final charge as the red one does, that's purely excuse me, that's purely what we're determining here. But let's look at the other aspects of it. At all times, the darker blue line is above the red line, which makes sense because with a lower resistance, you can have a greater current, which means you're going to be able to charge the capacitor faster. So for a given amount of time, you would expect this new RC circuit to be at a higher charge. So it makes sense that we're above there. Oh, that's great. Ooh, this is a tricky one. This is tricky. I like this one quite a bit. Okay. Buckle up for this one. Switch in the figure has been closed for a very long time. Ooh. What's the charge in the capacitor? How long after the switch is open would the charge in the capacitor decrease to 10% of its value? Let's talk about it. Okay. What's going to happen here is once the capacitor is fully charged, okay, that 2 microfarad capacitor, once that gets fully charged, no more current is going to flow through the right-hand side. No more current is going to flow through the right hand because you're going to reach a particular potential difference there. Now, if you notice at the top here, we have a 60 ohm resistor here. And after a long enough time passes, that means the current that remains, any current that's going to remain here is going to cease to flow through the right-hand side, because once you load this up, you don't have any charge, any current that can flow through here. I mean, capacitor is literally a gap, right? I mean, it's like an open switch in a way. And once you've compiled enough charge there, I mean, charge is not jumping across the capacitor plates, although it could. If you raise the voltage up enough, you could actually have that. You could have spark it and stuff, and then strangely enough, you would have current flow, but that's kind of beyond what we're talking about here. So if the right-hand side is now cut off, basically, because it's reached its potential difference, then the circuit just becomes the 60 volt in series with the 40 volt. And so I drew that over on the right here. The 60 volt, the 60 ohms, the 40 ohms are in series, so we add them up, and we would have a current of 10 flowing through the circuit there. 60 volts for the 60 ohms, 40 volts for the 40 ohms, which means the right-hand side, because it's in parallel, is also at 40 volts. Now, because no current flows to the right-hand side, the 10 ohm resistor is basically ignored, because the resistors don't do anything if current's not flowing through them. It's not like capacitors where they get charged and they can maintain a potential difference. The only reason why potential differences exist in resistors is when current flows through them. So based on 40 volts, we can work out how much charge is on the 2 microfarad capacitor. We use the capacitor equation. The capacitance is 2 times 10 to the minus 6 times the 40 volts, and we get 80 microcoulombs. Okay, so that is the initial part of the question here. So let me reiterate a couple things that are very important about this. If we say that the switch has been closed for a long time, then what happens is the capacitor starts to be charged, okay? And once it reaches its full amount of charge, which will be when it gets to 40 volts, the right side is not really part of the circuit in terms of current flowing anymore. So if we work out what's across the 40 volts, then that's what's across the capacitor here. All right, what's the second part of the question? How long after the switch is open with a charge on the... Okay, so if we open up the switch here, the 60 ohm capacitor, the 60 ohm resistor and the battery are now disconnected. So they're not part of it. So basically what you have is you have an RC circuit now that consists of a 2 microfarad capacitor and a 50 ohm resistor, because the 40 and the 10 are now in series. They're in series now, okay? Because the entire left side is gone. Once you open that switch, that left side's gone. And so this is a little weird, because when it's closed, there's a parallel configuration between the 40 and the 10 and the capacitor. But then when you open the switch, the current's just going to flow on the right loop there. The left loop is disconnected, and then it's not parallel anymore. It's actually series now. Because remember, think about this in terms of what it means to be parallel in series, right? If I leave the 100 volt battery and I go through the 60, I have options, right? I can go through the 40 or I can go through the 10 to get back to the battery. Okay, well, if I open the switch, I'm just traveling in a loop now. I don't have options anymore. So therefore, the parallel configuration is gone. Anyway, the equivalent resistance would be 50. The RC circuit is therefore has a time constant of 50 for the resistance and 2 times 10 to the minus 6, so 100 microseconds. And I want to know how long after the switch is open would the charge on the capacitor decrease to 10% of its initial value. So that means our charge is 0.1 times Q naught. I'll plug that in here. The Q naughts drop out. You solve for T here, and we get 230 microseconds. So it looks like we're a couple time constants later, which makes sense because, right, the second time constant is 13%. So if we're at 10%, we're a little bit past 2 time constants. That's a good one. That's actually a pretty good one here. Let me think. There's one more thing I wanted to say about this. What's happening? The first problem, you only got two problems in your homework. Okay, you got a couple days, so I didn't try to make it all crazy. Just made it real simple. Took a couple problems, and it basically reflects exactly what we did in the class. So as you can see here, you have a little bit crazier combo of capacitors and resistors. So you're going to have to work out what the combination of those are, which are anyways a nice review for your exam because you're going to have to be able to do that stuff. So that's very similar to the example we did in class. And this one down here is that we have the capacitor in the figure below is initially uncharged. The switch is closed at t equals 0 seconds. Ooh. So immediately after the switch is closed, what is the current through each resistor? So check this out. Remember what we said about this capacitor here. As soon as the switch is closed, what's the potential difference across this capacitor here? It is 0. So as soon as the switch gets closed, our current is going to flow through this as if there is no capacitor there. So that's how you want to solve part A. Part B, what is the final charge on the capacitor? So now this is assuming that we leave the switch closed for an extremely long period of time, and then we use the same logic from the last problem there. Okay, once the capacitor gets fully charged, that is just like the last problem, and then the right side of this circuit doesn't have any current flowing through it because the capacitor has reached its final charge, and no current can flow once it reaches final charge. So that's kind of a good problem. So part A is basically let's assume the capacitor is not there, and part B is let's assume the entire branch on the right is not there. And what you'll get from that is you'll get what the potential differences of the parallel configuration is here. Once you get the voltage of the parallel configuration, that would be the voltage of the capacitor, and you get your charge from that. All right. Ooh, look at this one here. I'm going to just go through this and tell you the stuff that I like. Now, your test is going to be structured in pretty much the same way that the first one is. All right, so you're going to have a series. You're going to have a series of. Boy, those were obnoxious jokes. As soon as we got into the 21st century, like I heard those jokes so many times. Remember that thing that happened last century? Yeah, that was crazy. Like, okay, I've heard that joke 50 times already. Thanks. All right. Anyway, you're going to have a series of multiple choice questions that are conceptual in nature. Okay, and there's no proper way to prepare for that other than quiz yourself with the questions that are in the study questions here. And one of the things I'd recommend you do is to go through, all of my slides because here's my thought process when I make a test. With the conceptual questions I'm going to ask you are largely derived from my lectures. So I have a lot of questions I ask you, right? And because I think that those concepts are very important. And so along those lines, you want to keep that stuff in mind. But my idea for exams are I don't generally want to completely surprise you with things. I don't like doing that. I don't like throwing something at you That's totally new and different. Not to say I won't do that. I might do that, but it won't be like the entire test is like, what class am I in? You know, it's like, for some reason, all of my math classes were like that. We tab the class and study everything and do the homework, and we get the test, and I'm like, what class is this? I'm like, professor, is this the right? You sure you got the right class? Like, I don't get this. I don't know. I do like occasionally having maybe one or two questions that makes you extend the concept, right? Because there's a reason for that, right? The idea is that if you really truly understand the material, then you could take something you've never seen before, apply the things you've learned, and be able to solve it. I mean, that is an excellent way to assess a person's ability. It's not good to make an entire test that way because you're going to make a lot of enemies that way. And I'm not interested in making enemies or friends or anything, but I still want to be a little fair. All right. Anyway, in terms of questions, you're going to have to, the free response questions, I'm loving number 5 here, right? You got a distribution of charges, and they want to know what the potential is at point A and the potential at point B. That's a good question. Right down here, you got 2 point charges. What's the potential difference between A and B? Ooh, I like this one quite a bit. Now that's going a few weeks back, but that's a great question. Some of these are 10's good. I'm probably going to throw you a combination of capacitors. You definitely want to freshen up on parallel and series everything, right? Parallel and series everything. Capacitors, resistors, well, that's everything, but still. Make sure you know how to do all that stuff. Great. 11's great. 12 is a great question. 12 is going to make you think. 12 is going to make you think. And let me see here. Is this the right question now? Wait a minute. Okay, potential difference is that switch is open. Isn't there another part to this question? No? What? Well, okay, here's the good question here. What happens when the switch is, well, when it's open, they want to know what the potential difference across C and D is, right? If you close the switch, what's the potential difference across C and D? Anybody know?
Zero.
Too late. I already got it wrong. Too late. You had 5 seconds to answer the question. You all got it wrong. What's the answer? If you close the switch, what's the potential difference across C and D? Sounds like a test question, people. 0. You bet. It's 0. 0. Okay, I like these questions. You know why? Because you look at it and it looks really complicated, and then the question's actually really easy. And that's just part of the mind games that I think are good for character building, But anyway, a better question would be an interesting question, which I might do. Now it's like the seeds planted in my head. What's the equivalent resistance with the switch open versus the equivalent resistance with the switch closed? Ooh, that's different. I got 4 kids, Ashley. You know how that goes. You got kids too. All right. Keep them guessing. Keep them wondering. Okay. You always start your sentence with "if you love me." Always start the sentence with "if you love me." No, I'm just joking. Don't do that. That's not nice. Let's see here. Ooh, I like 15. I like 15 because it's very easy to figure out what the equivalent resistance is here, right? Very easy to figure that out. But it's more interesting to think about, oh, this is actually not hard. Never mind, forget it. I thought 15 looked cool, but it's not. Never mind. It's okay. It's just not that bad. What else here? Oh, these are all great. Man, people study this thing. These are great questions. These are great questions. I like these. Kind of upset I already used them for the study questions. Now I'm going to come up with new ones? Ugh, too much work.